I'd like to thank everyone who came today and the organizers and Clemens, who I forgot to put on the title page. Okay, so I'm talking about hyperbolic angles in Lorentzian prelink spaces. So I'd do a very quick introduction to Lorentzian prelink spaces. They have been introduced today already. I will define comparison angles and angles, do the triangle inequality of angles, then the monotonicity comparison, and the equivalence of these two definitions of curvature bounds. Then the space, the continuity of angles, and finally, if there's enough time, I will do the space of directions and stuff like exponential and logarithmic map. So this is joint work with Clemens Simon. And yeah, let's start. Okay, a Lorentzian prelength space is just these things we've already seen, the time-like relation, the causal relation, and the distance. It's called strictly intrinsic whenever for two causally related points there is a causal curve between them where the length is the tau distance. And such curves are called distance realizers. We also need this time-like geodesic prolongation thing. That is, every distance realizer can be extended a little bit on both sides, such that this extension is a distance realizer near the two endpoints. So this is basically that maximally extended geodesics are defined in open intervals. Okay, shortly, comparison triangles. Time-like triangle, just three time-like related points and distance realizers between them. A comparison triangle, the same thing in a comparison space, like a constant curvature Lorentzian, two-dimensional Lorentzian manifold. And the comparison triangle is just a triangle in there with the same time distances. That stuff always exists. And for points on sides of this, if I have a point on the side of this triangle, I can create a point on the corresponding side of the comparison triangle by just requiring the time distance to be the same. Okay. Yes? No. Shall I draw something? I mean, I have 3 points here, the connections between them, 1 point on here, and I just draw the same thing and measure the correct distance here. And that's it. Okay, we defined hyperbolic angles. So what should a hyperbolic angle be? Well, physical intuition would be I have two particles flying around. They meet at some point. And what's the speed difference of them? And the correct measure for that would be the hyperbolic angle. For Lorentzian manifolds, that's the standard definition. Like the absolute value of the inner product of the normalized initial velocities should be the hyperbolic cosine of the angle. So what to do on Lorentzian prelink spaces, because such options are not available. We just build on that and say, I have a comparison, I have a triangle, I get a comparison triangle, then I can measure the angle in the comparison triangle. So yes, if the constant curvature space we make the comparison triangle in has curvature k, this is the k comparison angle. Okay, and this can obviously also be done at the other points of the triangle. Like I have a triangle in x here, and I measure the hyperbolic angle here, here, and here, and that should be the comparison angles. For k is 0, we don't care about the k. The sine, yes, there are some inequalities which depend on which of these three angles one is at. Therefore, we define the angle like in these two, the sine is -1 and here it is +1. And the sine angle is just the sine comparison angle is just the comparison angle with the sine multiplied onto it. Okay, real angles. That's now not for 3 points. We now have 2 curves. And now we pick points here, then this will form a triangle, take the comparison angle, and then take the limit as these points go in. Yes, we have, when choosing these 2 points, one has to take care that they are time-like related. Otherwise, this triangle is not time-like and we cannot form comparison triangles. Okay. We take the lim sub, then we call it the upper angle. If the lim sub is a limit and exists, we call that stuff an angle.
So you're always taking it to 0.
I always take it to flat. More to that in a moment. Sine angle, sine onto it. Like the sine of this angle, this comparison angle is always the same, and so sine. Okay, back to you. We used k as 0. If we use another thing, we would have come to the same result. And for C2 strongly causal spacetimes and C1 regular G time-like curves, the things are the same as in the definition I had before for spacetimes, for Lorentzian manifolds. Okay, an important technical result when dealing with comparison triangles or in triangles in comparison spaces, we have some monotonicities floating around. Like I have a triangle. Now I keep 2 of the side lengths fixed and vary the third one. If I do this, all 3 angles have the same monotonicity. Namely, if I make the longest side length longer, the angle will increase. If I make one of the other 2 side lengths longer, the angle will decrease. One can also view this as the reverse triangle inequality gets more into an equality or an inequality. Okay. Now, one of the main results of our paper is the triangle inequality of angles. Like we have 3 curves meeting in a point, like this maybe, or maybe like this. And then we measure these 3 angles. And then they satisfy the triangle inequality of angles. Like, well, under some technical assumptions, like if all 3 point into the future, or if one of them points into the past, there's no problems. Maybe we need to assume one angle exists. But the thing is, if the middle one points into the past, there is a counterexample, but one can fix this basically with curvature bounds and this geodesic prolongation. And yes, these are all cases. Okay, so 8 minutes in. Okay, I'll skip. Okay. Another thing we did is monotonicity comparison. It's an alternative definition of curvature bounds, time-like curvature bounds. So one of the definitions is triangle comparison, which is there. We assume X is covered by neighborhoods U, where tau is finite and continuous, and we have these distance realizers between any two time-like related points. And for any triangle, like there is a triangle, we have 2 points on 2 sides, then one makes a comparison triangle, takes comparison points for these 2, and then one measures this side in comparison to that. And if one always has that one is bigger than the other, time-like curvature is bounded below, and in the other case it's bounded above by k, and k is the curvature of the constant curvature space where one has realized the comparison triangles. Now, the new version is monotonicity comparison. It's a bit different. We have to assume that between any time-like related points in U, there is a distance realizer which is time, and any such distance realizer is time-like. And now we are dealing with distance realizers, like I have 2 curves going there. I pick 1 point here, 1 point here. That's at parameter S, that's at parameter T. I can create comparison triangle, get the comparison angle, put that into the function theta, including a sign, and this thing should be monotonous. If this theta is monotonically increasing, time-like curvature is bounded below, and if it's decreasing, time-like curvature is bounded above. Okay, that's nice, because theta is precisely the thing. Sorry, I forgot one thing. There's one extra thing we have to assume, namely this thing, but if one looks at it strangely, it can be viewed as theta is kind of a little bit defined and still monotonous. Okay, what is nice is theta is precisely what one needs to define angles. So if it's monotonous, the lim sub is automatically a limit. And well, it's automatically finite in one of the cases. The sign is meddling with it because the monotonicity comparison had a sign, the angles didn't have one. Okay. Another main result of our paper, the monotonicity condition and the triangle condition are equivalent for locally strictly time-like strictly intrinsic spaces. Like the first 2 conditions should be the same, should be made the same by assuming them, and then it's okay. Okay, we also have semi-continuity of angles. Basically, we have distance realizers converging pointwise, meeting at a point such that comparisons, such that one can make angles. And then we have semi-continuity, depending on the curvature on the one or the other. And similarly, this time we cannot have the base points converging. We have to make them fixed. Then we even have continuity of angles under time-like curvature bounded above in some assumptions, or time-like curvature bounded below and geodesic prolongation. Okay. Space of directions. Basically, we have the triangle inequality of angles. That makes the space of geodesics coming from a point a semi-metric space. Okay, And then by modding out angle is 0, one can make it a metric space, and that's called this future directed time-like space of directions. Yeah, for strongly causal spacetimes, this is just hyperbolic space, because angles are basically just between vectors in the tangent space, and tangent space is Minkowski anyway. So there is also a kind of converse notion to this, like given a metric space, we can make a Lorentzian pre-length space which has this as space of directions, which is defined like this. It's the cone as a set, cone metric as D, this formula for tau, and yeah, causal and time-like relation defined correspondingly. Okay. For hyperbolic space, this is basically 0 plus the time-like future of 0 inside Minkowski space. And this equation for tau comes from Minkowski space, like S and T should be the distance to 0 from the comparison point, and the distance of P and Q should be the angle. Like there's 0, that's S, that's T, that's EPQ, then this should be tau of the 2 points. Okay. If one chains these two together, one gets something we call the future directed time-like tangent cone. Yeah, for strongly causal spacetimes, this is 0 union I plus inside the tangent space, if one likes to view it like that. The metric is not as I would prefer it to be. It is coarser than the topology on Minkowski for spacetimes for Lorentzian manifolds. Under some technical assumptions, we get reasonable stuff like space of directions is complete metric space. And under lower and upper curvature bounds, the completion is intrinsic, so both together makes the space of directions intrinsic. Okay, we have a relation between this tangent cone and X itself, namely the logarithmic map and the exponential map. Okay, the logarithmic map should be just given a point in the future of X in a locally uniquely time-like geodesic neighborhood. We should map it to the time-like tangent cone. With the T component should be the time distance, and the second component should be the unique distance realizer between the 2 points. Okay, this is just for strongly causal spacetimes. This is the inverse of the exponential map, at least a part of it. Similarly, the exponential map just the other way around. For R and equivalence clause of gamma inside the tangent cone, we map this to the geodesic gamma at R, where we parameterize that by tau arc length. Okay. Yeah, that's just the exponential map. And under this stuff, it's well defined. Okay, under some conditions, including curvature bound above, logarithmic map is continuous. An exponential map under this technical stuff, and curvature bound below it is, we proved it's continuous. Okay, that's it. I still have 2 more minutes. Yeah. There are more slides. So go outlook. Well, one can use these hyperbolic angles for a splitting theorem. Agam will talk about this, I think, on Thursday? Wednesday? Wednesday, okay. Okay, there is another, what am I pressing? There is another equivalent definition now for curvature bounded below using angles. That's Barrera de Oca and Solis. And recently we came up with another definition, namely the 4-point condition. It's basically the triangle inequality for angles in the future past future case, but with the comparison angles instead of the angles. This has a big advantage of not intrinsically requiring some geodesics to exist. Okay, that's it for me. Here are some references. That's, where is it? Where is it? Should work. There it is. That's this paper. That's this equivalent definition with angles. That's the original paper by Seemann and Kunzinger. And that's the metric case where all these equivalent definitions are in, or originally came from, probably. Okay.
Sorry, you put 2022 was that an update or was that?
God, why is that?